Hello, and welcome to my presentation about optimal control of cranes with geometric path constraints. My name is Felipe Barbosa, and this is a joint work with you and Lovely. Here, we deal with the problem of loading and unloading a ship as fast as possible. For a glimpse, let's look at Figure 1. Here, we represent a ship-to-shore crane handling a container between the ship and the shore. Here we can also see that there are different stack heights, which are our geometric constraints. This kind of problem can be hard to solve if we use time discretization, because we don't know the length over which the discretization is performed. Also, since the stack heights are a function of space, the constraints are nonlinear and non-convex. In this work, we try to make it less problematic by reformulating it and parameterizing it in spatial coordinates. For this, let's look at Figure 2. Here we have a two-dimensional schematic representing the trolley and the payload or the container motions. From this, we can obtain the equations of motion, which are parameterized in time. So, from this, we also have the state variables, which are the trolley position, y, the angle of the pendulum, theta, and the length of the rope, L, and their corresponding derivatives. Also, the time that a trolley takes to go from the initial position to the final position can be written as this equation here, which is the reformulation we mentioned. After this reformulation, the state equations become these ones here, which are parameterized in x1, which is the position of the trolley in our case. With the reformulation, the new state vector becomes like this one here, which has the time as the state variable. And also, now the time optimal problems becomes this one here in the box. The first consequence of this reformulation is that now the positions, velocities, and accelerations are now related to each other through the parameterization of the path. And also, the objective function here is now convex. A drawback of this new formulation is that now, since x2 here is the velocity of the trolley, it assumes the value 0 in the very beginning and in the end of our process. And this is problematic because it leads to convergence problems. So in order to overcome this, we calculate the time it takes to go along the first and the last iteration where they are supposed to be 0. We calculate this time analytically. And we do that by using the state equations before the reformulation and making some linearizations in these state equations. What we are doing now is evaluating if these linearizations are good enough for our problem. And after this, we are going to implement a controller and perform the experiments in a crane simulator. And after this second step, we are going to implement this strategy in an actual crane. With this, I conclude my presentation, and thanks for watching.